Okay, so we got to know the background. I think about 30 to 40%, 30% maybe you're familiar with the basics of coding, and some of you are from computing who probably have not exposed to the coding, but everybody would have heard Hamming codes, right? Okay, so what I thought, this was the kind of set of slides I created for initially, some part of it initially for third year students in networks to have some idea of coding and who don't have things, and so it was fairly low level, but the intention is to understand the real meaning behind some of these codes, what was done and etc. Okay, and then in the next lecture, after I formally introduce some finite fields, so then we can build up the theory in a much more logical way. Okay, so this will be here. I will be throwing some new things, but if it is not clear, you can just stop me and understand, and we can go through. What I will be using only a very simple binary mathematics, zeros and ones, and the exclusive OR function that I think everybody is familiar with. So that's a very beautiful theory. We'll talk about it. So this is the Hamming code, and partly it's kind of inspired by some of the fun underlying ideas of Hamming codes. Hamming codes have a lot of interesting properties, and if you come to know and if you start appreciating that, then you will never stop. Then probably all Adrish lectures you will watch, and you can actually understand coding in a much better way. Yeah. So the really purpose is to have a gentle introduction to history and working of Hamming code. I mean, history I don't do too much. Remember, Hamming was an engineer, like computer scientist working on the first computer in the Bell Labs at the same time Shannon was working on information theory in the other part of the same Bell Labs. And for Hamming, he those days, the when he was writing programs, it was all the computers were made out of magnetic devices. So I'll just come back to that one. Let's say the contents will be just to errors and erasure decoding of Hamming codes. So that way, what is error and erasure becomes pretty much clear with this thing, and some properties and motivations, and then I'll come back to general model point. These are all fundamental part that's in communication theory. So what is really so different in storage, the same coding concept? So just have a different view of approaching this problem can actually throw a more light. And so I don't claim that itself as a new contribution or something, but it's just a way of looking at it. So basically, I was telling you about the Hamming was an engineer. He was working on computer memories, and I think he wants to fix the bug that bothers him, because in those days the bug is a real bug. These computer memories have made out of magnetic relays. So if there is some bug sitting there, this relay won't operate, and then 1 will be 1 or 0, and then the whole program will go away. So he writes a code, in those days with a 7-bit, 8-bit memory. It was then after 1 day of work, no answer. So he wanted to fix that bug, and at that time he came up with this code of correcting one bug bit error. So if there is a fixed bug error happen, he could change it. So that's how actually came. So in some sense, it's a part of the memory. So the real, the Hamming code is one of the pinnacle of all the codes. Hamming code is the perfect code. This came out from storage. Okay, but whereas in last 10 years before, the coding theory was mainly to meet the Shannon's limit, and it is for communication. So you can see and we come back again. So you can see. So what do you do is that see this, let's say, have many interesting properties. We will now look at them in a little bit general way in this talk, and as a go about it. Okay. So let's take the length of the code. So normally, what's the parameters of this code? Again, I'll come back to that. So I now can assume now that I can easily talk to you about integers, and I don't need to be. So for example, now length of the code is always 2 to the power of m minus 1, where m is another integer greater than or equal to 3. So when n equal to 3, n is 7, and that is the first Hamming code that everybody is familiar with. And the number of information bits it can do is always 2 to the power of m minus 1. So in this case, in the first case, when m is equal to 3, it is 4, and the minimum Hamming distance for this Hamming distance for all that code is 3. That I'll come back. What is the Hamming distance? Is the number of positions they differ, and the error correcting capabilities it corrects for, and so possible dimensions. You would have heard this, right? You would have heard about this. Yeah. So basically, we want to understand actually what they are and so forth. Now, one example you see is that the 7-4 Hamming code, as I already mentioned, the code can be expressed as symbols over bit, and so it can act as a generator matrix. And again, generator matrix, I am not defining it precisely, but you can see that all code words, there are 16 of them, can be obtained as linear combination of these numbers, which is each time the code is zeros and ones. Okay, it's a bit, binary bit, and this is how it is there. Now, this is a matrix representation. So what I can do is I can have an information bit. So for example, my information. So if you have a code words, information bit of 4-bit, what does it really mention? All the information bits are any possible binary number. So 0 0 0 0 is one information, second one is 0 0 0 1. So you can actually count there are exactly to the power 16 different information bit. Now that gets mapped into a code word of length 7. How does it do? So for example, you can choose this load. So if you choose, that will be 1. So if the information bit in the first bit is 1, choose this. Second bit is 0, don't choose this. So depending on whether it is 0 1 or 1 0, you can choose and simply XOR, and that you get a code word. Now that can be easily explained as for example, information bit, you can represent it as I0, I1, I2, I3, like a vector of length 4, and that 4 times this matrix you get the code word, and that's what we do in the block code definition, but will be much later. But why did Hamming gave this particular code, this particular one? As you can see that this has another concept that comes in coding theory is a rank. That means basically if you take out this matrix and start looking at the how many for example, how many columns are needed to represent all other columns as a linear combination of them. So you can see that there is this column that has a 1 here and the rest of them 0. Okay. So and there is another one 0 here, there is 1, the rest of them 0. So you can see that the vector that I mentioned, that is 0, 1 and 1 is there. So that means with that this code has a rank 4. So that means that you do but why does he put it here? That was a question that people want to understand. I will go back and say do this here. So all code words of this code now can be explained in the figure, in the paper bureau, as in 4 information bits. So you can took information bits are A, B, C, D. Now A can go between 0 and 1, B can go with 0 and 1, C can go with 0 and 1, D can 0 and 1. So each position has 2 choices for 2 choices, 2 choices, 2 choices, 2 choices. So how many different things are possible? 16, 2 to the power of 4, right? So this is a simple combinatorial thing, and then of course you then have 3 parities that depends on all of them. So you can actually write down all the matrices like this. You can see that you put all here, A is 0, so B is half 0 here, and C you can see D changes 0 1 0 1, then C like this, and this is with in this slide with this A with 0. Next slide, A is the same thing as A is 1, and all parities are actually generated as a linear combination of these bits. Okay, and generally he gives. Okay, so using our result on XOR operation and the definition of parity that I mentioned, so any Hamming code word satisfies this matrix equation. So I take the multiplication rule as an AND function. The multiplication is 0 times 0 is and 1 times 0 is 0. So you multiply by with 0, any one of them is 0 is you get 0, and only 1 times 1 is 1. Exclusive OR is, you all know the same function, so you can now define that as this one. So the parity equations are generated with the things like P2 is chosen such that it is a parity of B, C, D, P1 is chosen with A, C, D, and P0 is chosen A, B, D, and Hamming chose this in precisely this way for the reason it will become obvious in a minute. So what he did was basically then one way to do is that whether how much it can correct and all. I won't introduce any theory and all, I will just go through. Let us say what happens to a single error. So once what you do, you choose A, B, C, D and then generate the whole code word sub length 7 and you transmit them on a channel. The other side you got a received word, and in the received word will have R1, R2, R3, and it could be one of them. So you observe them as zeros and ones only, but you don't know which one was transmitted. And so assume that there are no errors, okay, and then if there are no errors, we know, and assuming that the positions of A, B, C, D's are exactly A here, B here, C here, D, like here A, B, C, D, I can recompute P0, P1, and instead of that what I do, I use the same equations and I actually compute the parities in charge. And then of course for example this parity P0 which is R1 was generated as the sum of all these three. So but now I include them also together, and what you expect is if there is no errors you get all 0. That's quite obvious, right, because you generated the parities. See R1, if there is no error, R1 will be parity P0, this will be P2, and R4 will be P3. So obviously if there is no error you get all 0. Now interesting thing is what happens if there is one error. Now one error, if you say, that's where the combinatorics and other mathematics starts playing. If there is one error, how many different possible error it could be? It could be exactly n7 choose 1 is in all these positions. So there is no error, there is a bit there. All other places error could be in first bit, second bit, third bit, fourth bit, fifth bit, like that. And this particular thing that I mentioned, for example the parities, I now clubbed that as some kind of a syndrome, but I'll come back to that syndrome bit later. So now you compute it. Now if R1 happens, then I compute these equations exactly. It's basically recomputation of the parity, but include the parity itself. So when you do that, you get R1, you get 0, 0, 1, and R2 you get 0, 1, 0, R3 0, 1, 1. So now look at the binary representation of these things that you have found, and the precisely 0, that means no error, 1, 2, 3, 4, 5, 6, 7. It exactly tells you the 7th bit is in error, it tells you there's 7, 6th bit is in error, it tells you 6. So he arranged all this such that when you recompute it at that place with the assumption that there's only one bug could happen. I mean that's two bugs can happen, I'll come back, but let's say assuming that only one bug can happen, then when you compute this it exactly tells you which position error. So when you design the circuits you can actually use this y0, y1, y2 to really correct that bit appropriately and solve the problem. This is why Hamming used this version in the thing. So I mean we will come back, and when we come back things, there's many ways you could define. So this is how the effect of single error that Mott has. This is basically our said, but each of these 7 possibilities of having single error has a different effect on this. So that means what I found was if there is any single error happen in all this, and these are the only places that a single error could happen, either here, 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 and I work here, all of them are different. So if a single error happens, some kind of syndrome or some kind of a effect that I am seeing on it, like I test it whether what has happened, that tells me always distinct one. That means in order to recognize that there is, if whichever that is there, I should be able to distinguish all of this. Do you see that logic? Otherwise you couldn't do. For example, if this error and this error resulted in a same type of appearance like a syndrome, then I won't be able to say whether it is this or that, then I'm in a dilemma. But it so happened, for his luckiness, all of them are distinct. So this also tells you that some properties, that is error correcting. So I can say if there is one error happen, I can always correct it. So I know which one error that is, because I have demonstrated to you a constant thing. So we also know that at least one. So we need to know that, let us say, error is no more than one. Okay. So for example, what happens if it's more than one? So then I cannot correct it, I should be able to show. So the one really problem to understand this is kind of a minimum distance. This is means that when the code words are there in a space of length 7 now, because initially all code information bit is only 4 bits, that means there is only 16 different possibilities. Now these code will now be embedded in a bigger space of 7 bit number, 2 power 8, 2 power 7. So how they are apart in that extra space becomes an important thing. So now let us take R1 and R2, 2 bits are in error. Now you get, when 2 bits are in error, like this one, you do the R1, R2, so you compute this 2 bits in error, then you get this 0, 0, 0, 1, 1. But from the table, this also corresponds to a single error in R3. So that means you got an R1 and R2 error, I can't distinguish between R3. So if there are 2 errors happen, I can't decide whether there are 2 errors happened or 1 error happened, because I know already for 1 error it corresponds to R3. So we cannot decide if a single error or a double error. So the error capability cannot be, is actually exactly equal to 1, it can't be 2. So obviously 2 is not possible, it's big 1. So now then obviously if it is 1, of course now I put it sometimes you have a, let us say, what does it mean really to have a 1? I am just going a little ahead here. So that I haven't really talked about the distance metric space or anything, but sometimes if the minimum distance is either 3 or 4, you could still correct 1 error, because I'll come back to that, but it will become more obvious when I give a general things. But we can rule out that it is 4, and by considering in that particular one it's actually 3 in this case. But in this particular one you have there, but the same argument you can do it for any m and try to do that. So it's a bit of a thing. So probably I can explain this a bit more thing how we did with Achilles Venn diagram. So Achilles came up with this Venn diagram approach. So you have 3 circles here, for example A, B, C, D, the information you put it under the innermost part, and the P0, P1 and P2, the parities are chosen such that P0 is a parities of all the bits come under this pair, and P1 is a parities of all the bits come under this pair, and so on. So you can see that with this one works very well. So the decoding thing, we proved that the minimum distance is 3. This means that we can correct any single error. So you take for example semi-received word and you can contribute syndrome. The decimal value of the binary, this I already explained to you. You must be wondering why the complex code is a this kind of a complex arrangement is basically to exactly find out which bit was in error. So what's a parity check matrix? So parity check matrix in that case is basically a restatement of the parity equation in the matrix form. So you have a h here, so you actually, in other words, you can, whatever the received word you multiply by h, that becomes 0, and so you give that. So received word now happen to be code word plus error word, then you check with the received word is h times c plus e, that is same as h times c plus h times e. We know that h times c is chosen to be a parity check matrix, that gives there is no error, because all the code words as a thing that becomes 0. So what you get is a error syndrome. So if you look at this all possible with the syndrome computation, you could see the same things. Now the errors can happen in all these positions. The syndromes actually gives you the same table. So to correct one error, distinct syndrome. So basically this idea, why this is basically what I told you is how you can generalize it to any code. Once you have the syndromes are there, what I need to do is basically I need to compute the syndromes corresponding to the typical errors that happen. So after that you look at the syndrome and find out the corresponding error pattern and simply XOR with the received code, so you can do it. But the beauty of the Hamming codes arrangement is that this particular, he does not need to do this step because the syndrome directly tells him, oh, correct first error, correct second error, and so forth. That is what the Hamming did, and this in fact he also explains how he did that, and in a sense closely equivalent to this one. So let us try to look at this one. So for example, any code word that has been constructed in Hamming code, you know, there are 16 possibilities, but they all adhere to this parity equations. So now let us say an error happens, okay, or let us say something, let us say a particular bit is erased, for example a bit is erased, okay. Can you now recover it? So if one bit is erased, then you have two choices. You can go here and look based on these three, put the parity here, you are all right. Okay, now I erase, let us say 2 bits in error. I erase A and D. Can I recover? No? So let us take the same case. So assume that we have 1 0 1 1. So what's the parity here? 0 here. Okay, so this is, let me put 1 here, then parity here 1. Okay, so you can have, this is the one code, it's already there. All the parities are 1. Okay, see there, good. So it's all one word. Okay, but to make it interesting, we'll make one of them 0 here, then this is 1 1 0, that's correct. This is correct. Now this is 0, this one is 1. Okay, 1 1 0 0, correct. The top right one is this one should be 0, correct. Okay, so now let us say 2 symbols have been erased. So let us say I erase this and this. Can we do it? Obviously, because you can recompute them, right? 1 1 0 same, this is also 0. But what if let's say you have all 3 have been erased. Can we recover? So what was it before here? 1, is it? Okay. Let us say only these 2 have been erased. Can we recover now? Yes, you can. So you can see that any 2, you can always, any 2 symbols have been erased, based on this property you can recover. So here actually all that comes because the minimum distance is 3. So any up to minimum distance minus 1 symbols have been erased, you can recover. But some part of 3 also can recover. For example, here this is 0, let us say this one is 1, yeah. But some part of, let us say you go here, you can recover even sometimes. But sometimes this is what called erasure thing. So this is 0, and this is 1. Erasure decoding. Okay. Whereas in the errors one, as you can see that if there is more than one errors, you will have a problem in deciding. So in fact this is a very interesting way of actually understanding, and the decoding also I explained using syndrome decoding in some sense. Now let us get back to how many erasures you can correct. That is what I did. So you can say get back to Venn diagram. So basically you will notice although you can sometimes recover 3 erasure patterns, you will always be able to recover 2 erasures. So you can always be able to do the 2 things, and that proof comes from the Venn diagrams there. So any 2 bit missing bits can always be recovered because you have 3 different equations in using the sphere. It's very interesting, right, this particular one. In fact, if you look at this in Achilles has a very interesting talk on this, and he even uses this in machine learning later, this can be used especially because of the this difference between erasure and error decoding. Now let's next continue some interesting aspect of the Hamming code. Hamming code is a perfect code. Why? So we have decided that now the length 7, that is so it is k equal to 4 initially. So all possible, you can start, see there are totally each time is then there are 2 to the power of 4 different one, and all that will be encoded into length 7 that has 2 to the power of 7 different ones. Okay. So around each code word I am allowed to look for the patterns that are at a distance 1, 2 and so forth, and create a sphere. So given a particular code word, whatever, so for example, it's suffice I take only the first 0 code word, that's right, where it's A, B, C, D, everything is mentioned, then this particular word is a valid element in GF 2 to the power of 7, F2 2 to the power of 7, because that's a 7-bit word, and that are at distance 1 to the thing. So the distance 1 is, the distance concept here is very simple, which is the number of positions that differ from the code, and it will also can be defined as a Hamming weight. Will come back later, but so look at that, and there are exactly 7 of them. So you can see that there are 7 words surrounding that, and I can do the same thing around each of these code words. So you take a code word, which is another one. We may have, say for example here, so this is if I remember, let us say first one is P0, right, P0, P1, A, P2, B, C, D, right. So you can see that if for all these different possible 2 to the power of, there are totally so many code words, 2 to the power 4 code words, and I can start counting the number of words which are at a distance 1 from another. And I'm also, because that I can correct 1-bit error, so if no 2, for example, I put this particular word which is at a distance 1 from code word can never be in another sphere, because if that is another sphere then that will contradict, right. So totally there are about, so now let's count them. So how many words are there in this one? 7, 1, 8. So there is 2 power 3 words are there, and there are 2 to the power of 4 of them. So 2 power 4 times 2 power 3, if you use 2 power, that exhausts all possible words of length 7. So that's why Hamming code is perfect code, because you can actually compute. So number of code words around with distance is 1, total number of words less than or equal to 1 now is this. So this covers the entire space. So when he really come up with the code, he laid out this code in a perfect manner, and this is one of the perfect code, and this applies for example, whatever logic I did for length 3, so if it is m, you increase for in this case m equal to 4, then it will be 2 power m minus 1, which is 15, and 11 3 code. Next will be 2 power 5, which is 31, then minus, pardon? It's basically minus 5. How much? 2 to the power of 5 minus 1 is 31, right? So what is this? 26 and 3. So in all of them, the way you count them is basically the space in which you work will exponentially increasing, but still everything is perfect. And this is the one of the major class of codes that are perfect. And he did it were working on a computer storage like computer systems, and then within an year or so Golay came up with other two codes. One is it's a Golay code which is 23 11 and 6 code, no 5 code. Then there is also another one in GF which is based on finite field 3, GF3. So interestingly, these are the only classes, 3 classes of code which are perfect in this universe. In whatever way you can think of in mathematics, there are no other perfect code, these 3 ones, and Hamming is one of them. This is the kind of thing. So this is what the kind of things will come. So Hamming code is a perfect code. We'll illustrate this, that. So now let's come in with the kind of a approach for our the coding for communication. So we have a source. So normally, especially the communication view is quite familiar. I think those who are already come from communication field, you know that, you've been told. So you have a source, and then you encode the source from k bit to n information, and really you use some kind of a modulator or whatever based on the communication device you have. Lots of blocks will be there in thing, but most of them can be absorbed in one group called send. So you got an encoder and you get send, and a send could be using some other modulation technique. You send it onto the channel, and you have a receive and decoder, and you get back the sync. So this is the coding model. So you got some information and send and receive. Now what happens in coding for storage? Now the thing is that you have a source of information, you again still encode it. Now the function that changes is store, and that store itself, what you do, where you store is now can be generalized. In case of RAID and all, is pretty obvious. You will be using perhaps the devices within the one computer, or in some cases another. But in general, you get stored into a network, and the network is connected by so much of with bandwidth and latency and others, right? The actual operations happen. The other case is read, and read this read is based on the input IO read and whatever the distributed system. So you can do that, and once you read it, you decode it, and you actually consume it in some way. So this view, for example, here in the communication view, you send the bits in some way, and there will be some kind of a delay coming there, but the delay is always instantaneous, because it will be some few milliseconds. It's not much, because whenever you send in a communication, the other person is doing in a real time. So the delays are always small, whereas the problem with the network thing is that delays can be many. So for example, you may store once and you may keep on reading many times. So delay can be from maybe 1 minute to infinity. It can, sometimes we want our data, whatever that we have stored, to be there for perpetually, all the time. So this is some of the things that the people should think. For example, today we have a data, and how long that data should stay. So in 2005 and 10 years ago, and companies came up, let us say, giving you an email service for you. So you got an email things, and have you read any, what they guarantee you? Your emails will be there in their servers. But then they moved, when you move from their traditional storage devices into a distributed one and all, you need to give some kind of a guarantees, whether what's the probability with the failures and those kind of calculations. And it turns out that using this erasure coding things actually gives you a much better control over that mechanisms. But this is another type of thing. So how you store it depends on those calculations. So I think this model for coding, and so if you closely watch, and I don't know whether people have studied much in this. For example, there is also something called delay tolerant computing. So for example, where the send and receive involves having a purpose. For example, if you want to communicate packets from going into Mars and come back, and sometimes the delay can be several minutes, and how do you actually design systems to work in that category? A similar type of problems will probably apply to storage devices, because sometimes I store and I can read anytime. So it's basically there is nobody like sender and receiver, it's always reading from the same devices, and I need to get the same view every time I read. So but are there any fundamental things that affect storing here from such consideration? I don't know. So it's just a kind of thinking for in a thought. Yeah, it's not a big thing. I just you made out of that in this. I'm not sure whether this has been formally discussed in research community or not, this kind of a modeling part. But on the other hand, you would understand why we are getting into these ones. So I kind of with the Hamming code I introduced why the interesting part of the coding theory, that it's a perfect code, and so that's how kind of a motivation to study more. So maybe in the next lecture we will go on to some formal definitions of codes, block codes, and so forth, and we also need to know some finite fields and other stuff. We will continue with that. Any questions and things to maybe? So for those of you who don't have a background in finite fields and all, do you think this will be difficult to follow? I mean, is anybody so that's what I want to say. How do you feel this? I mean, nobody would say that it's difficult to write that, but I want to say which aspects. So if you have any comments and a thing to start with. Okay. Pardon?
Hamming codes are clear.
Hamming codes are clear. Okay. Even though this modeling part is clear, so zeros and one. Yeah, okay.
That's regarding the perfect codes. How do we perceive that figure that as if we are placing those 16 number of the bonds inside a bigger bond?
Yeah.
So there must be some space left out in between the bonds.
No, that's what it's not there. You can see that it looks. I mean, I wrote down a ball like that, but the objects. So in this particular phase, there are only 2 to the power of 7 different objects. So I take one object, which is a code word now, and I look at all other objects which are at distance 1. So there are exactly 8 of them, no more, no gap in that. So under every code word there are 8 of them. So if you really count them, so there is already a 2 to the power of 7, you exhaust all the words, so there is nothing left. So there are no code word, no vector which is in between it, but which may not be the true for other codes. Some other codes can correct one error. That means, so I also come to a kind of a proof that if a particular have a code, then if you construct a sphere of radius around say 3 around each of this code word, and if the vectors in all of them they are distinct, then I can always correct one error. So what I do is that my decoding algorithm will be simply look at the input word and check which sphere that it belongs to, and then just simply decode, okay, that was the code word. Now this idea, that is, I have a sphere around each code word, and then I locate the received word to be in one among them, and then I decide to be decoded to the code word inside that associated with that sphere. This is an assumption of decoding. This idea will work because in practice happening one error, probability happening one error is much higher than probability happening 2 error. So when you are correcting, you will assume that okay, one error is happening. So probably if you read more of Adrish other decoding algorithms in future things, all these things are precisely mentioned, but many times it's not the code that is correcting, it is the actual our decision that is deciding decoding in favor of the code which are at a minimum distance from this code word. This is called maximal likelihood decoding, and this idea is that. And so many people who work in coding theory just from purely parameters, they only look for the code word with minimum distance. They may not even have a practical idea that this is why it is decoding is because it works in practice in this way. Yeah. So you know that kind of that's an engineering decision, sometimes often ignored also. Yeah.